I don't know. Now, on the other hand, what about the other one? There's a repeated root here. How about the minus 1? The other minus 1, you get, well, I guess we talked about that already. It would be a natural log of x over x. All right. Oh, I do have one with imaginary exponents. Woohoo! So here it is. So x equals 0 is a regular singular point. Yeah. So I'm working what these are out in terms of the Frobenius solution. Eventually I get to this. I plug it in, right? Here's my initial equation. It works out to r squared plus 4. So I have indices of plus or minus 2i. So I plug the plus or minus 2i into my recurrence relation, which I get from everything except for the initial equation terms, right? And yeah, so then I've got a recurrence that involves complex arithmetic to sort through. So I got, yeah, a1 is a naught times 1 minus 4i over 17, and then a2 is this, which works out to that. And yeah, that's about as much as I could tolerate at the moment. So then I wrote this. So we have x to the 2i, 1 minus 4i over 17 times this. So this is the this is from the a naught. This is from the a1. This is from the a2, obviously. And so you can, where did my, I've still got the x2i out here, right? Remember what that is. That's exponential of the log of x to the 2i. It's actually what? Cosine of 2 log x plus I sine 2 log x. That's all wrapped up in this x to the 2i power. But on the flip side, this is just the other part. So what I'm doing is I'm collecting together the real part of everything else and the imaginary part of everything else. Then it's a simple matter to multiply the real part of this times the real part plus the imaginary part of this times the imaginary part. Actually, that gives us a minus because I times I is minus 1. And so just like you've seen before, multiply out the real expansion of the complex expansion of this times this complex expansion. And that gives us this thing down here. Again, real, imaginary. Over here you've got imaginary real, and real imaginary from these from this again from this right here, which if we expanded x to the 2i, again it's cosine 2 log x plus I sine 2 log x. Does that make sense? I mean, what I'm saying? No is okay, I think. Yeah, you can still say no. So yeah, that's the solution, where I have only had the patience to work out like the first couple terms in a sub x and b sub x, right? So if I was to ask you a complex Frobenius problem, I would probably have the common human decency to only ask you for like the first 4 non-trivial terms or something, which I think is what I found here, basically. The first, well, 1, 2, 3, maybe the first 5 non-trivial terms here, something like that. I don't know. I think to be decent, I should say, I have found the solution up to quadratic order. Maybe that would make sense. Even that doesn't quite make sense, right? Because, I mean, this is quadratic, like the a of x is quadratic, right? But it's quadratic times cosine, right? And it's quadratic times sine. Is that quadratic order? I mean, what is that? I don't know what it is. It is a complex Frobenius solution is what it is. The calculation that follows differs from our initial example in one main aspect. I put in the exponents before I look for the recurrence relation. And so here, this is my remark to emphasize what I told you already today. Don't do what I do here. This is in some sense a cautionary tale. This is what it looks like if you solve the recurrence, if you solve the initial equation to start with. I get my exponents are 0 and minus 2. And then, again, 0 is the larger one, so I have to do that first. And so that's what you get when you plug that into there. Then you collect things together eventually. I just have, for me, it's just easier with the R than with actually plugging the R in. I don't know. You can do it either way. You get the same answer, but anyway, after the dust settles, there's your recurrence relation. That's got to be 0 for every j larger than 2 or equal to 2. And you also get these guys out here. This says that A1 is 0, and this says that A sub 2 and A sub 0 are linked. Right? This says that A sub 8 times A sub 2 is equal to minus 2A naught. That says that A sub 2 is equal to minus 1. Why don't I just scroll down? Yes, A sub 2 is minus 1/4 A sub naught, which I was working out in my head for some reason I don't understand. A sub 1 is 0. Yay. And you see that there's a duplicity here in the sense that like we're linking from plus 1 to minus 1, so like 2 separated or linked, right? So the fact that 1 is 0 and the fact that this links every 2 forces all of the odd coefficients to be 0, right? And all the even coefficients, well, recurse, 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 recurse. Eventually you find this pattern down here. And there you go. That's the 0th Frobenius solution for this problem. Like so. Now, the second one is weird. You have to do something a little bit different. This minus 2 and 0, they're differing by an integer, right? They're both integers. They differ. But it's like if, I'm trying to remember. I'll tell you in a second here. I forget. You know, usually we have these solution methods, right? And we get a quadratic equation, like in this case the indicial equation, which tells you what goes on, right? And that's kind of it. But the Frobenius method's weird in that there's actually like 4 or 5 cases, depending on how you enumerate them. And the cases are more carefully stated for you guys. It's one of the places where I think your textbook is probably, it's got a little bit more than my notes probably here. This is theorem 6. Well, I've got the blue book. I let the grader have my old and superior edition. In the blue version, it's page 468. It's the Frobenius theorem. It's theorem 6 in chapter 8 for this book. Do you happen to have your book? You do? Yeah. Is it page 468, theorem 6?
No, it's 461, theorem 6.
Ah, 461, theorem 6. Thank you. Well, we have solved the mystery. Very good. Thank you, thank you, thank you. But here, basically, it says, if x naught's a regular singular point, there exists at least one series solution of the form 30. That means the regular Frobenius solution, what we've been finding in here, where R is the larger root of the associated indicial equation, and this series converges, blah, blah, blah. Now that's the starting, it's starting comment. Now later, oh, come on. Oh, section 8.7, finding a secondly. So you find theorem 7, I'm going to estimate 468.
Good job.
Ah, theorem 7 on page 468 of your text. Form of a second linearly independent solution. And here we have cases. A, if R1 minus R2 is not an integer, so if the difference between the indices is not an integer, then basically what it says is you repeat the method twice. You find 2 Frobenius solutions of the type I've shown you today. However, if they are repeated, then you get one regular Frobenius solution and you get another one that's the log times the first one plus a Frobenius solution. So it's like a log times the first one plus another one for a repeated root. And then, part C, if the difference between them is a positive integer, then again you get one Frobenius solution, and then the other one is some arbitrary constant times the first solution times a log plus another series. So like you just got to look at this and try to absorb it for yourself. It's a little bit subtle what happens when the indices differ by an integer. It's just unpleasant, or when they're repeated, it's unpleasant. I mean, it's not surprising to us, right, that when they're repeated, something weird happens. We're used to that. It's the idea that when they differ by an integer, something weird happens. That's kind of surprising to me, right? I don't know if I have enough time to discover why that is with you. at the moment. But so this problem right here is such a problem. But this one is kind of useless because the extra terms, the log terms, don't turn out to be necessary here. So this is actually an accidental problem where you just get two Frobenius solutions. You don't actually need the log. So this example is not optimal in terms of showing you the weirdness of the method, unfortunately. See, so this one actually, the -2. Oh, actually it is kind of weird, but it's not the kind of weird I was hoping for. Anyway, so here's the general solution for this problem. It just, you end up getting a sort of a Cauchy Euler type solution for the other one. So that's the Frobenius method. Here's a derivation of why the differentiating by a root works. And yep. So guys, what's next? I'm supposed to give you guys what? Take-home test 3. So what's on take-home test 3?
Everything since the clock.
Everything before test 2? That's what you should want, right? Yes. No. So the energy analysis, I'll ask you something about that. Remember the diagrams we drew? Phase plane? I'll try to get you guys to learn a little bit more about the nature of singular points. There will be a token, series problem, Frobenius problem probably. And then the rest of it's going to be partial differential equations, which we'll get into next time. So,
That's going to be due like
whatever I said.